Welcome everybody to today's NCTS and Academic Sinica Distinguished Lectures. We have great honor to have Professor Alice Chang and Professor Paul Yang from Princeton University to give today's lecture. And Professor Zhang, she was trained as an analyst, but then later on she used her very strong this analyst ability to study geometry problem, and she has done very many profound results. Recently, she is more concentrated on conformal geometry, and she has received lots of awards. Include the National Academy of Science of the U.S. and Academic Sinica's fellow. Okay, and also lots of other honor. And she was an alumni of NTU Math Department. She was also awarded of Distinguished NTU Alumni. And so she also spent lots of time to do service, including she has served the chairman of the department in Princeton University, and also the vice president of American Mathematical Society, and she promoted lots of activity for women mathematicians. She and Professor Yang, they donate a scholarship in NTU. So 张扬奖学金哈。And so probably I spent some words in Mandarin. 那张老师他那个，我们如果在网络上面搜寻呢，你可以看到很多他的访问，包括有这个我们台大杰出校友的那个的影片，好，然后还有这个中研院有访问那个就是数学传播有一个访问稿是访问张老师跟杨教授的。另外呢 ，and also there is a documentary film on this her class on Professor Zhang and a few very distinguished women mathematician from their class， 叫做学数学的女孩们哈，所以大家可以在网络上搜寻更多他们的资讯哈。那 so Professor Zhang is going to talk about let me see compactness of conformally compact Einstein manifolds. Let's welcome Professor Zhang.
It's a great pleasure to be here, especially after the pandemic. And also, it's the first time I'm in this new building and this new lecture hall. It's a great pleasure. Okay. I will talk about a problem which I have worked on many years. And actually, you may have heard part of my lecture before. I hope we are still making steady progress toward the eventual goal. Okay, so the title of my talk is called Compactness of Conformally Compact Einstein Manifold. So I'm talking about a joint work mainly with my coworker Yuxin Ge, and also partially with Qing. And the recent progress is made jointly with Yuxin Ge, and then there is a separate progress made with Paul and Rubin Zhang. So what is the problem? The problem is the following. Suppose I have a manifold, compact manifold without boundary, say MD D-1, and with a metric. We ask, when is this manifold the boundary of an Einstein manifold? And then what does it mean by an Einstein manifold? For example, the hyperbolic manifold. It's non-compact. So the boundary is at the conformal infinity. So that means it's the boundary, but in a conformal compact sense. So that means there exists a defining function rho. Okay, I need to learn that. Okay, rho. Okay, defining function rho defined on X, and such that if you multiply by this non-compact manifold G plus Einstein times this defining function, that restrict to the boundary is your H. Okay, so this is a problem called conformal filling in. Given this manifold, you try to conformally filling it in. And this problem arises in the ADS-CFT correspondence, and it's a problem proposed by Babatsida and also Wheaton in around 1998. And mathematically, this problem is also connected with lots of work on geometric consideration of the boundary behavior of asymptotically hyperbolic manifolds. It turns out this manifold is definitely hyperbolic, asymptotically hyperbolic. So the outline of my talk is straightforward. I will first give an introduction, a brief survey, and then I will talk about how to set up the problem. Okay, so how to set up this compactness problem. And then I report some statement of the compactness problem. And the main thing is, this is a problem which is dealing with conformal invariance. So all the conditions should be modular the conformal invariance. So this is statement of perturbation theorem and uniqueness theorem. And then I talk a little bit about some recent work with Yu Xinge, where we get some more concrete compactness theorem in the dimension 3 plus 1. 3 plus 1 means 4-dimension, boundary dimension 3. And then maybe I sketch some idea in the proof, okay, main ingredient. So start with definition. I already mentioned given a manifold M with boundary M. So I usually say X is D dimension, M is D minus 1 dimension, and I have a defining function, which rho is positive on X and equal to 0. We call it defining because D rho is not equal to 0 on the boundary. And then it's conformally compact. If G plus is not compact, but multiplying by this rho square, it becomes compact. Okay. And then, because in this definition, there's the ambiguity of what is a defining function. There are many choices of the defining function, and given a defining function, you can multiply it by another positive function to make it defining function. So that means in this case, the boundary is defined up to a multiplication of a positive function. So we say the boundary is a conformal class of H. It's only the conformal class is determined, but not specific defining function. Okay, so I usually, later on, I denote n equal to D minus 1. And if we choose a specific Einstein manifold, and that's called Poincare-Einstein, that means Ricci of G plus equal to minus NG plus, then we call it conformal compact Einstein. So in this lecture, I denote it by CCE. CCE means conformal compact Einstein. Okay, so the first remark is, CCE manifold is asymptotically hyperbolic. That means it's metric near the conformal infinity has sectional curvature minus 1. Okay. And then the other thing is, it turns out, given such a setting, you can have a special defining function. We call it a geodesic defining function, which can be chosen so that in an asymptotic neighborhood of the manifold, it's a product structure. So if this is boundary of X, and this is X, and then it's a product structure. So that means the gradient row with respect to this compactified metric is identical to 1 in a neighborhood. So there's this product structure. It's a good coordinate function. So the choice of such function exists in an asymptotic neighborhood. Okay, so here are some examples. The first example is the upper half space with Euclidean space at the boundary, and then the hyperbolic metric. So in this case, if you multiply y squared by gh, you get a flat metric which is not compact. So it's conformal Einstein, but not really conformal compact Einstein. So, but this is our model case. And actually, this is the space we will pay special attention to, in the sense that later on, when we have blow-up argument, we would like to see if blow-up happen, then the limiting space is this model space. Okay, so that's the model space. And then the second example is, of course, we choose the hyperbolic ball, Euclidean hyperbolic ball. And then we choose the defining function to be 2 times 1 minus x over 1 plus x. This choice is not obvious, but if you choose this row, it's a special defining function, and GH is written in terms of this way. Okay. So in this case, restrict to rho equal to 0, you get the sphere as conformal infinity of hyperbolic space. And we remark that in this case, there is also a fact, that is, if you think about this rho, this is actually exponential minus 2r, where r is the distance from 0, hyperbolic distance from 0 to x. Okay. So this defining function, rho, log of that, rho over 2 over r, is the hyperbolic distance. That's something to keep in mind. And then there's a third example, which is an interesting example. Suppose we have boundary, which is S1, the circle of length lambda, and cross S2 with the product metric. It turns out when lambda is small and the number is specific, 1 over square root of 3, then there are 3 conformal filling in. So with the same boundary, you can have different way of filling in the hyperbolic, the Einstein metric. The first one is you think about you have S1 that stay, and then you develop S2. You fill in S2 with the hyperbolic 3 ball. So the conformal space filling in is S1 lambda cross B3. And then it turns out in this case, the metric is the hyperbolic 4 space. Okay, so that's one filling in. But it turns out that when lambda is small, there is another way of filling in, and that is you begin to develop S1, and you're filling it in with the B2. Okay, and then somehow S2 stay. So in that case, your topology is R2 cross S2, and then your filling in is what one calls ADS Schwarzschild filling in. Okay, and it's studied by physicists, and it has specific form. And the other amazing thing is that in this case, again, this is a filling in for each lambda, but for lambda is less than 1 over square root of 3, it turns out that there are two different choices of the mass for the same conformal infinity. So this is the non-unique filling in, the famous example of Hawking page. Hawking page. Okay. Okay, so now I briefly mentioned the non-existence results and the uniqueness result. Okay, so the first well-known, actually that's the fundamental tool of this subject, is the ambient metric filling in of Pfefferman-Graham. Pfefferman-Graham did not fill in given the boundary, the entire space X. They say in an asymptotic neighborhood of MD minus 1 cross 0 epsilon, there exists such Einstein manifold. And in the original work, they actually assume H is real analytic. So their things is a power series expansion. And this work has been extended by Gursky and Sakihide in the 17 to smooth H. Okay. And then there is another piece of work by Graham and Lee, Robin Graham and Lee. And they say that if H is a small smooth neighborhood perturbation of the canonical metric on SD minus 1, then there exists a filling in. And one can extend this work a little bit. For any Einstein manifold on the boundary, you can fill it in. And on the other hand, there is examples which says on certain boundary, you do not allow conformal filling in. So in particular, in a work of Gursky and Han, and Gursky, Han, and Strauss, they say that, for example, for the sphere S7 or S4K minus 1, K bigger than or equal to 2, and then they say in that case, you can find metric on the boundary, which is positive scalar curvature, and which does not allow B8 as conformal filling in. Okay. So that's an example. So notice that their example is the metric they choose to be of positive scalar curvature is not in the connected component of the canonical metric. There's other connected component. And one key thing they have used in their work is actually a result of Qinjie and Jack Lee. And what Qinjie and Jack Lee prove is if the boundary Yamabe class is positive, that means in this conformal class, you have a metric which is scalar curvature positive. Then Jack Lee constructed filling in. If it's already a CCE, then you can have a metric which is in the interior, which is also of positive Yamabe class or positive scalar curvature. Okay, so based on this fact, they use some work of Gursky and Han and Strauss, use some topological work of Lawson and Gromov. Okay, so now because we, in view of Gursky, Han, and so on the result, we wonder what happened if we are on S3. Okay. So if the boundary is S3, then the open question is, if a metric on the boundary has positive scalar curvature, does it allow a conformal filling in? That's the question I'm trying to address. And what is the difference of S3 versus S7? Okay. In particular, in this case, the class of the class of positive scalar curvature metric is path connected. in 3 manifold. And also the index formula for non-existence of Gutsky and Han does not apply. In the S3 setting, you need some kind of spin structure. So this does not apply. Okay. And so in order to address this problem, we think we need to first study compactness problem. And that is, we hope that the compactness would lead to degree theory and lead to existence. Okay. So now let me say what is the compactness problem. The compactness problem I'm trying to address is if you're given a sequence of metric on a boundary which is compact, do you have a representative in the interior which is a compactified metric or your Einstein metric and which also is compact? We know it's not unique, but you can still address the compactness problem. Okay. And so your restriction is GI restrict to the boundary is the given HI. So this is sort of a Dirichlet problem. You hope the boundary condition control the interior compactness. But to make this statement more precise, we need to say, what do you mean by modular class or the conformal class of HI compact? That means you need to choose a representative of it, which is compact. And then what does it mean by GI forms a compact? You also need to address what is the representative in that conformal class. You are saying it is compact. Okay, so, and now let me say that the main difficulty of the problem. Okay. So suppose that on, say, we are back to 3 manifold. Then if we have this compactification G, which is equal to rho square G plus, rho square G plus, pointer, I actually do not see. Okay, so here, okay. And then we know it has an asymptotic expansion. The expansion is d rho square and plus the boundary metric and plus G2 rho square plus G3 and so on. Okay, and it turns out in this case, in the 3-dimension, 3 plus 1 dimension case, the G1 is 0 and G2 is an information of GH. Given H, this G2 is sort of a receipt of H. But G3 is so-called non-local condition. G3 is actually the normal derivative of the receipt. Okay. So we know that in PDE, the famous problem is Dirichlet to Neumann condition. If you, from the Dirichlet data of a harmonic function, you want to know, does it decide it's a Neumann data, or if the Neumann data decides the Dirichlet data, Dirichlet to Neumann problem. So this Neumann data is a non-local information. That is, it's not determined by H. Okay, so you need some other condition. You note G plus together with H decides G3. But on the other hand, suppose we only know H, we do not see G3. This is one can derive it because it's conformal to Einstein. You use Einstein equation, okay? Because G plus is Einstein, okay? Sure, yeah, it's actually a work of Robin Graham, okay? Yes, asymptotically, in an asymptotic neighborhood of the boundary, conformal infinity, is a power series expansion, okay? And so, okay, So I remark H and G3 determine the asymptotic behavior of G, okay? And again, it's a work of Pfefferman-Gran and also of Picard. Again, Picard works on smooth manifold. Pfefferman-Gran works on real analytic manifold. Okay, and now, as the conformal infinity is determined up to a conformal class, so we want to study what are the invariants. Okay, so now I'm trying to recall some basic invariants, well-known invariants in geometry, and the first invariance is called Yamabe invariance. You take inf of the metric in the conformal class of the integration of the scalar curvature normalized by the volume. So this is the invariance on the boundary. So that means the value only depending on the conformal class. And in the interior for manifold with boundary, you also have conformal invariance, and usually you add a multiple of the mean curvature. And it turns out there is another famous conformal invariance when the dimension D becomes higher. So by the way, dimension D equal to 3, in that case, if you have positive Yamabe class on the boundary, there is only one class, and that's S2. So the problem is doesn't make sense. So we work on dimension D bigger than equal to 4. So in that case, there is another quantity, so-called the Weyl curvature quantity. Okay. Weyl is a measurement of how close the metric is conformal to Einstein, to Euclidean metric. So the Weyl has a pointwise, it's a pointwise conformal invariant. So the Weyl of D over 2 power integration is a conformal invariant. So now we want to set up the problem. So we have a boundary metric H, which form a compact family. And it looks like it's natural to choose H to be the Yamabe metric on the boundary. So constant scalar curvature metric on the boundary. And then the other attempt is what is a good representative of the interior conformal metric. And you want to say Yamabe metric too. But the problem is the Yamabe metric on the interior restrict to the boundary is not the Yamabe metric on the boundary. And actually you don't know what that is. So this is, so that means that in order to get good control of this metric, we should not choose the Yamabe metric. We cannot afford to choose. You do not know how to control GY from HY. Okay. So instead, we make a choice of the representative through some second-order PDE, and which comes from scattering theory of hyperbolic metric. And that's what we call adapted metric. Let me define the adapted metric a little bit later, but state the theorem first. Okay, so with that in mind, we have two theorems. Okay. One is called perturbation compactness theorem. So that means that suppose we have a sequence HI, which is compact, okay, on the boundary. And the Yamabe constant of that is bounded away from 0, positive scalar class. And it turns out that you have two equivalent conditions. The first is if the interior Yamabe D over 2 power is small. Or the equivalently, if the Yamabe constant on the boundary is close to that of the standard sphere, then the adapted metric I'm going to define later, whose boundary metric is HI, is compact. Okay. And one thing I like to address here is, it turns out 2 point and 2 double point are equivalent. Okay, so that means if one assumes one automatically get the other equivalent. And this is not obvious. It turns out the Yamabe constant is close to the sphere. Then later on, I'm going to tell you how to see the vial in the interior tends to 0. But for vial tends to 0, you get to say the boundary must be already close to the sphere, and that requires the uniqueness part of the theorem. Okay, so a consequence of this theorem is a uniqueness theorem, which I'm going to state now. Okay, so application of this perturbation theorem is a uniqueness theorem. So the first uniqueness theorem actually people have worked on a long time is if the boundary is the standard sphere, is the hyperbolic ball the unique conformal filling in? And the answer is yes. But the proof is quite hard at first when you use positive mass. In the late work of 2003 by Qinjie using positive mass. But then later on, there is a different proof by Dutta and Jafahiri, which I'm going to introduce later, which establish the ball as the unique conformal filling in. So at least when the boundary is the standard sphere, you have unique. But as a result of our perturbation theorem, we actually say that you can extend this uniqueness theorem a little bit for metric in a small neighborhood of the canonical metric. So in other words, for this metric H to be very close to HC, canonical metric on the sphere, there is this Lee and the Grant theorem, you know, there is a CCE filling in, but we say there is a unique CCE, even in that neighborhood, that's unique, okay? And the reason why this can be proved from our perturbation theorem is we have compactness. So we push this extension. The one which is constructed by Lee is in a perturbation of the hyperbolic metric. And our compactness theorem says, if you are going to converge, the filling in must be in a neighborhood of the hyperbolic.
That you imposed either condition, right?
Yeah, yeah.
If either of the condition fails, are there examples that there are no compactness for the?
There's no, on the sphere, I don't know, but we know there's non-uniqueness. We know there's non-uniqueness. As I say, Harkin page says.
The compactness.
I don't know. I don't know, especially if the boundary is S3. Okay, but we know that when the boundary is not S3, there is non-uniqueness. That's the difficulty. Okay, so this is a phenomena on the sphere, on a perturbation of the neighborhood, the topology comes in. Do I answer your question? Okay, sure. Okay, but it turns out we can extend this uniqueness theorem also to the situation of S1 lambda plus S2. Okay, so what we are saying is when lambda is very big, then this S1 lambda cross S2 has a unique CCE fill in, that is S1 lambda cross B3. When lambda is very big. Okay, recall that when lambda is small, this is not true. Okay, even for the same lambda, there are two filling in. So this result is a consequence of the compactness theorem. And the key fact is, in this case, when lambda go to infinity, the Yamabe constant tends to Yamabe constant of the canonical metric. We use that fact. And so the strategy of the proof apply also to this uniqueness theorem. Okay, and now let me at least state one statement of a general compactness theorem. So the general compactness theorem says, again, we assume boundary metric is compact, and then we add an assumption. That assumption is while L2, I mean 4 dimension. So while L2 is bounded, and then I add some topology assumption. The topology assumption is H1 and H2 is 0. Homology group is 0. Then we say this sequence of this adapted metric is compact. Okay, that means work in progress. Okay, so that means we already have a preprint, but it's not published yet. Okay, yeah, still, yeah, technical report, you say it. Okay, so that's my theorem. Okay, so and now let me say that what is going on, what are the ingredients in this program and the difficulties, okay? So the first one is, I would say there are 3 ingredients in the proof. One is, one want to control certain type of conformal invariant in the interior by the conformal invariant on the boundary. Okay, and in other words, we are trying to compute, for example, the Yamabe constant in the interior by the Yamabe constant on the boundary. Okay, and the early work of Li and Qin says if the Yamabe invariant on the boundary is positive, then the Yamabe in the interior is greater than equal to 0. It doesn't say it's bound a portion of Y of Mg. And so our first step is to say, okay, to give a quantitative estimate of that. And why do we need that? Because the Yamabe constant is in fact Sobolev constant. So later on, when we want to have something compact, we have an iteration scheme, and we need to control this Sobolev constant. So that means if this constant is greater than delta bounded away from 0, or Sobolev constant is bounded away from 0. So that allows us to iterate. And this seems to be an innocent statement, but actually it takes 3 teams to work on the problem and each add a piece. And that is the work of Gursky, Han, and Chen, Fang, and Lai, and ourselves. Okay, so we prove this, control this constant. So that's the first ingredient. And the second ingredient is I need to adjust what is the adapted metric. Okay. Adapted metric is something, given the boundary, this is developed by Graham and Zosky when they studied the scattering theory on CCE manifold, and they use that to define these co-GJMS operators. Okay. So what they do is the following. For each S, say between n/2 to n, one solves the Poisson equation on XD, on this space. So there's a solution. And then through this work in this scattering theory, one knows this V has this asymptotic expansion, rho to the n minus s power times f. This f is on the boundary is any given f. Okay, so this is a Dirichlet data, and you capture by this f. And then the main thing is what's left over has at least power rho to the SG, and G on the boundary is called a scattering data. That's called scattering theory. So this whole theory is developed. Our own observation is that in this case, if you take F to be positive, your data is positive, then you can see the Poisson equation V of this equation is positive. Okay, so that means you can now begin to take this V to the 2 over n minus s power. Remember, V is rho to the n minus s, so V to the 1 over n minus power is rho. So you have the leading term is rho. So you have rho squared G plus. That's called what we call adapted metric. Okay. So this is the sequence of metric. We take F equal to 1, and which has a good property. For example, if you take S to be n plus 1, this S actually could be n over 2 to infinity. That's a typo there. So if S is equal to n plus 1, then F equal to 1, then the metric is the so-called Jack-Lee metric. The Jack-Lee metric is the metric which we compute if the boundary scalar curvature H is positive, then this metric has positive scalar curvature. That's Jack-Lee metric. What? Okay, because you are asking the idea of Jack-Lee, and we all ponder about that. Why did you consider this? And that's the linearized operator of the scalar curvature equation. So he's comparing that. For that particular index, S equal to n plus 1. Yeah, linearized, yeah. Linearized equation of the scalar curvature equation. Okay. Okay, so, I'm sorry, I probably have scale. Okay, it turns out if S is chosen to be n over 2 plus 1 half, then the metric, this family of adapted metric share the same property as Jack-Lee's metric. And for example, it's totally geodesic. And if the boundary metric has scalar curvature positive, then the interior is positive. And in our early work, we work a lot on this family of this adapted metric. We thought the natural choice is S equal to n equal to 3. And in that case, you need to modify the metric because the original Poisson equation doesn't work. Because in the index, there's a modular class of metric called Pfefferman-Graham metric. And we work a lot on that choice of linearized of this adapted metric. But later on, our difficulty is the following. If we choose S equal to n over 2 plus gamma, and if this gamma is, say, less than n over 2, gamma is greater than 1 half, then in that case, our difficulty is we do not see why the G and star, this metric scalar is positive, but why is this finite? We do not see that. Okay, we see there is a positive lower bound of GRS, but we do not see how to control the L2 norm of the scalar curvature, and even assuming value in L2. So eventually, we choose our adapted metric to be when S equal to n over 2 plus 1 half. Okay, so this metric is not totally geodesic, but empiric. So what's the good property of this metric? it's scalar flat because the way we choose it. And it turns out in this case, the boundary scalar positive imply the mean curvature of the metric on the boundary is positive. Okay. And then this growth of G star equal to rho square G plus still have this, the gradient of rho less than equal to 1. Because later on we want to create a compact family, so we want to control the distance function. And then the advantage of this is we look at the Gauss-Bonnet. The Gauss-Bonnet formula used to be here plus the scalar curvature square. But in our case, the scalar curvature is 0. So we only have the negative term. And then the price we pay for the metric to be not totally geodesic, then the Gauss-Bonnet has a boundary term. But that boundary term turns out to be the scalar curvature on the boundary h times the mean curvature. Notice this is a positive term. And minus something of h cubed. So as a result for our metric, we have Ricci L2 bound and the mean curvature L3 bound on the boundary bounded by the data. The information we assume via is finite, and then we assume the scalar curvature H is a compact family. So this is bounded. So that's the biggest advantage. And then we use some common property of this adapted metric. It's conformal to Einstein. So it satisfies this equation, which is Bach flat, okay, Bach flat. So this is a little bit technical, but it's an elliptic system. So the elliptic system tells us we gain. That is, if once we assume G star is in C3, then it's actually in C3 alpha. Okay, we gain. And this gain also eventually leads to the Ricci decay of the limiting metric, which I will come back later. Okay. Okay. So that's the second ingredient. And the third ingredient in this subject is something called volume non-collapsing inequality. So it turns out in the work of Dutta Jawahiri, and later on, the work was modified and expanded by work of Li, Qing, and Xi. What they prove is the following. They say they work on a more general setting, but in particular apply to CCE setting. So suppose we look at T is the hyperbolic distance. Okay. Then we know the volume of G plus on a ball vice the volume of a hyperbolic, honest hyperbolic ball. That distance is always less than 1, less than equal to 1. But what this Li, Qing, and Xi says is you actually have lower bound. The lower bound is bounded by the quotient of the Yamabe constant. Okay, so in particular, if your Yamabe constant is bounded away from 0, you have volume non-collapsing. Volume non-collapsing. Okay. And also, if this is equal to 1, so suppose on the boundary I have the sphere, the Yamabe constant is 1, then the whole thing, this is less than equal to 1, and it's equal to 1. So the Gromov-Bischoff theorem tells you it's the ball. It's isometric to the ball. So that's what we call LQS inequality. Okay. Okay, so now I come back to say some proof of this compactness theorem. Remember, my compactness theorem is I have boundary data, I have L2 non-via, I try to say the family is compact. And so there is a difficulty of this local quantity and the gauge invariant because we are dealing with Einstein metric. And our strategy is to use epsilon regularity and blow-up analysis. Okay. So the first step is by contradiction. Okay, so it seems the only way to do things is by contradiction. So we assume the adapted metric. We first prove by contradiction that this sequence of metric GI has uniform bounded curvature. And suppose not, then we rescale it so that the C1 curvature of the bound is 1 at some point. And then the rescale metric begin to converge in the Gromov-Hausdorff sense to a limit. So we first using the step 1, we using control of the Yamabe constants from the boundary to show that this sequence have uniform injectivity radius lower bound. And then step 2 is use the epsilon regularity to show the metric begin to converge in some Hausdorff limit. And the third step is the hard step. The third step is to show that this sequence, this metric has, after we normalize it, it's at a curvature equal to pi equal to 1, and that pi begin to converge. And then we worry that the converge is going to the boundary. That's called boundary blow up. That the sequence begin to blow up on the boundary. We will use a boundary Liouville rigidity type theorem to say no boundary blow up. I will say a little bit more about that. And then the last step is we use our topological assumption to say that there is no interior blow up. Okay, so that's the outline of the proof. If I'm not too much, I'd like to say a little bit about how to prove there is no boundary blow up. Okay, so it's already gone. Sorry. So how do I return? How do I return to the previous page? That's the later. This is going back.
Going back, yeah, going back.
Yeah, yeah.
You have two things.
Yeah. Oh, this is the last page. Going back. Yes. Good. Yeah. And then go back. And go back. Yeah, this here. Sorry. Thank you. Okay. So the first remark is, if this GI is rescaled and its boundary is rescaled, then the boundary metric converge to the standard metric on R3 because we assume the boundary HI is compact to start with. So I have to rescale it to the boundary. So the limiting metric, in this case, the conformally infinity is the standard R3. Yeah, because I'm talking about no boundary blow up. So I have this PI as a marking point and rescale around that point. Yes. The converge is in the mark point sense. Okay. If it's interior, then there's no boundary. If it's a boundary blow up, then we use that mark point. Okay. So Okay. So here I say something about the perturbation theorem. Okay, I'm saying the perturbation theorem part is easy because LQS inequality tells you that if YMHI tends to YS3, then the limiting metric has Y square equal to 0. So in that case, we already know it's the hyperbolic metric. Here I say a few words about the proof of the perturbation theorem. So now let me say the proof of the main theorem, the step 3. So I'm trying to say there's no boundary blow up. Okay. So suppose you have this sequence, which is have a bounded curvature blow up, curvature blow up, you rescale it. That's called GI bar. Okay. And now we only know the vial L2 norm of GI is bounded because that's scale invariant. And now this rho I bar will converge to some rho infinity because we know its gradient is bounded by 1. And so we are in the case, the limiting metric is again conformal to Einstein. That's called G infinity plus. And the key thing we want to say is because our vial L2 norm is finite, the scaled metric has curvature decay. And that curvature decay is 1 over x to the square. This square is not important, but we need a positive power here. So we have Ricci decay for the limiting metric. Okay, so the real theorem we have proved is the following. We say that we are in a situation of a space x infinity, and with Euclidean 3 space R3 as the conformal infinity, and it's conformal to an Einstein metric. And we assume it's a complete metric with boundary positive Yamabe injectivity radius, which we prove. And the conformal infinity is the Euclidean space. And the distance function is less than 1, the scalar is 0. And if the Ricci has this decay, then the metric is flat. G infinity is flat. The Einstein metric is the hyperbolic space. That's the real rigidity theorem we prove. Okay, so we have this condition. And so how do you prove this? Okay, the proof is you want to prove something is hyperbolic. The tool is use Gromov volume comparison. You want to prove the volume of the boundary of the ball vice the volume, this means surface area, in the hyperbolic metric tends to 1 as t tends to infinity. So remember our inequality, we try now to prove the right-hand side tends to 1. Then we apply Gromov-Hausdorff, Bishop-Gromov. So how do we prove that tends to 1? So we first think about define GT theta equal to both tends to infinity. The denominator and numerator tends to infinity as t tends to 1. So t tends to infinity. So we look at its compact part. So we look at the e to the exponential minus 2t g plus. Then the volume is the same in this compact metric times et over 2. And then the volume of the hyperbolic thing, real hyperbolic thing, similarly defined is sinh t over d minus 1. So as t tends to infinity, these two terms cancels. So you are now going to compare the volume of GT theta to GHT theta. But that guy tends to S3 because it's the standard hyperbolic ball. So to prove star, it amounts to show for this compactified metric, the volume tends to that of S3. That's what we try to prove. But how do we do that? We do that by considering a metric which is conformal to it, and that is the following. Is the following. So we have this ball, which is the hyperbolic ball. And we have gt is 4 to the e to the minus 2t, and then g plus metric. Okay, and on bt, this is the hyperbolic ball. T is the hyperbolic ball. But we have another metric which we define to be gr theta, which is e to the minus 2r of g plus. What is this r? This r should be the same as our rho square. So our rho square, rho over 2, log of rho over 2 is equal to our r. Okay, so remember that in the standard model case, this r is the same as t. But in our case, we have two competing metrics. One is this from this Einstein metric. One is with our this G star metric, and this is defined by this way. So what we are going to do is, if we have a t here and a gamma t, and using this GT ball, GT metric, I don't know if I use T or something like that. Okay, GT metric, we try to estimate its volume. We compare it with the metric gamma R and the GR bar there defined. Okay, these two metrics are conformal to each other. So we are comparing the volume of one to the volume of the other. So that means we should compare its conformal factor. And that conformal factor is exponential r minus t. We say that r minus t will be very close as r and t both goes to infinity. And that's the strategy. And so that means we begin to consider what is this psi during the growth of psi. And the growth of psi is expressed into this scalar curvature equation. And the scalar curvature has Rg bar equal to 0. So we look at this simple PDE and we begin the estimate. And the estimate, the key estimate is to say that this, we begin to, this previous equation, we want to multiply by psi and integrate. Okay, and when I integrate here, there's a gradient psi square, but then there is a boundary term. And that boundary term is psi d normal. And we are saying that this is boundary happen on the boundary of this sphere, and that, so you cut it by this ball, and then this happen on here, a two-dimensional space. And you want to say that's diminished, not important. And it turns out that's the hard step where we use Ricci decay. Okay, we use Ricci decay to say that term is not important. And then we estimate the energy. The energy is scalar times the volume form. And then the psi 6 power is also, because of the conformal class, the volume form. And then the next thing is to say the scalar, because we are so close to the boundary, so the scalar is close to 6, the standard case. So it's a 6. So And then the volume is control of GR is controlled by GT. So the offshot here is the following. We have a Sobolev quotient, the gradient square over psi 6 on R3. And then Sobolev embedding theorem tells you for any psi, there's a lower bound. That's the Sobolev space for any bound. And what we are trying to say is actually there's an upper bound, and that upper bound is the volume. Okay, so from 1 to 4, you can see 1 to 4, you have 6 times the volume divided by volume to the 1/3 power. So the whole thing is this volume to the 2/3 power. And that 2/3 power is comparing now to that S6, S3. Okay, so the offshot is this squeeze of inequality tells you that psi is the extremum function for the Sobolev embedding. And that pushes the volume to be the same as the S3. It's greater than S3 and it's upper bound by S3, so it's S3. And that shows that the Gromov-Bishop theorem says it's the hyperbolic space. Okay, and that's our proof. Okay, that's our proof. Okay. And now let me finish my talk. Sorry, this going up and lower confused me. Okay, sure. Okay, so let me say what are the open questions, okay? So the open question is, here I make 2 assumptions. One is on the boundary, one is on the interior. Both are conformal invariant. Does the second conformal invariant, the via L2 norm, bounded by the first conformal invariant? Okay, that's the question, open question. And it's a hard question. We know that when the ADS Schwarzschild example says when the Yamabe constant tends to 0, they are metric, the via L2 norm go to infinity. Okay, that's not a counterexample of this statement, but that does show there's a delicacy in the proof. Okay, but on the other hand, when we use this assumption, we only use it to prevent boundary blow-up. It turns out, in this case, in the 4-dimensional case, in the interior blow-up, this via L2 norm condition follows. And that's the work of Chigger and Neighbor, by the work of Chigger and Neighbor. So it's not clear if this condition is needed in the boundary blow-up also, but we do not see the proof yet. And the other thing is I want to make a remark of a high dimension case. It turns out in a high dimension case, the same proof as we did works for no boundary blow-up without assumption on via part. But the difficulty in that compactness theorem is we do not know how to impose suitable interior topological condition to make interior blow-up not happening. And that's where we are now. Okay, so thank you for your attention.